Greetings of the day. I'm Dr. Raghuram Mohan Reddy, Associate Professor, Department of Mechanical Engineering. Today's topic is Electro discharge machining Part 2 under Unconventional Machining Process. Okay. These two are the course learning outcomes of the today's topic. First one, understand the electro discharge machining. Second one, understand the abrasive electro discharge grinding. Let us discuss the basic non-traditional machining process of electro discharge machining. So before that, we briefly discuss the whole non-traditional machining process. So the whole non-traditional machining process is categorized into three main branches: mechanical, thermal, chemical, and electrochemical. Under mechanical, ultrasonic machining, water jet machining, abrasive water jet machining, ice jet machining. In chemical and electrochemical machining, chemical milling, plasma chemical milling, electrochemical machining of milling. Now we are discussing the thermal category. Under this, the first one is electro discharge machining, electron beam machining, laser beam machining, ion beam machining, plasma beam machining. So far we have discussed the different fields of electro discharge machining. Under that we have discussed electro discharge grinding and abrasive electro discharge grinding. Okay, so now we are going to discuss abrasive electro discharge machining. Abrasive electrical discharge machining, in short it is AEDM. Abrasive electrical discharge machining is a hybrid process based on EDM, that means electro discharge machining, where free abrasive grains such as silicon carbide powder are added to the dielectric liquid. Okay, so here the abrasive particles will add on to dielectric fluid medium so that it will be just like a slurry. Okay, so that is nothing but abrasive electrical discharge machining. Right. Now look at these elements of abrasive electro discharge grinding process. Okay, so here in abrasive electro discharge grinding, it is divided into two main phases. One is grinding phase, the other one is electro discharge machining phase. Okay, so in grinding phase, again it is with MA phase, that means machining by abrasion. So usually through grinding, the abrasion will be done. Okay, right. In electro discharge machining, the corresponding phase is EDE phase, that is nothing but electro discharge evaporation phase. Okay, usually it will be in the form of plasma. Okay, in grinding, the MA phase will be in the form of abrasive. These two will get together to form an abrasive tool. Okay, so here this abrasive tool is a cathode and workpiece is anode. Between these two, dielectric fluid medium will pass, and the gap between abrasive tool and workpiece is nothing but spark gap, where the spark will generate it will be usually below 0.01 millimeters. Okay, right. Now look at this. Abrasive electrical discharge machining (AEDM) is a hybrid process based on electro discharge machining, where free abrasive grains such as silicon carbide powder are added to the dielectric liquid. Okay, so here silicon carbide powder will add to this dielectric fluid, that is dielectric liquid. Okay, so this is a hybrid process, right? In addition to major EDE thermal phase, MA assistance is added. Already we have discussed here. See here, EDE phase is as usual in electro discharge machining, but here through this grinding process, the MA phase machining by abrasion, because of the abrasive particles, the machining will done through machining by abrasion, that is MA phase. Okay, the energy is carried by the plasma channel in case of EDE phase, and also by abrasive grains for MA action. That's what we have discussed here. Okay, the total energy is carried by these two components: plasma phase component in the EDE phase and abrasives in the machining by abrasion phase. Okay, right. Now look at this abrasive electro discharge machining system. Okay, right. Here through this channel or some arrangement, dielectric plus abrasives are supplied to the workpiece and tool. Here the rotating tool rotates and the workpiece travels towards left or right based on the requirement. Okay, so at the time of this machining process, since this is a hybrid process, dielectric fluid medium consists abrasives. Okay, so through this nozzle, dielectric and abrasive particles will be supplied constantly or circulated between rotating tool and the workpiece. Okay, see the machining media consists of dielectric and solid particles as indicated in this figure. Okay, so here the tool is rotating, okay, about its one axis, and it can traverse up and down. Okay, feed plus vibration plus orbital motion. Okay, so here the tool can move up and down and it can rotate, and at the same time it has orbital motion. About any arbitrary point it can move. Okay, right. Here the spark generated between the tool and the workpiece. Okay, so this is the spark. Okay, right. As usual, here the DC power supply is connected to tool and the workpiece. The tool is connected to the negative terminal and the workpiece is connected to the positive terminal. Here the tool is cathode and the workpiece is anode. Okay, so here the main point is that the machining media consists dielectric and solid particles. Okay, So dielectric plus abrasive solid particles. So these are the solid particles which has sharp edge, but in terms of microns, its size, and dielectric fluid medium. Okay. So here, because of the tool motion, at the same time, because of this abrasive particles along with this dielectric fluid medium, the machining process will take place. So that's why it is a hybrid process. Okay, right, right. In abrasive electro discharge machining system, let us discuss the mixing. Okay, mixing silicon powder into the dielectric reduces the electrical capacitance across the discharge gap by increasing the gap size. Okay, mixing silicon powder into the dielectric. See here, this is silicon powder, let us say. So this is dielectric fluid, which reduces the electrical capacitance across the discharge gap by increasing the gap size. As a result, better dispersion of sparks and improvement in the discharge characteristic, especially in the machining of a large workpiece. Okay, so here let us focus on the result of mixing silicon powder in dielectric fluid medium. Better dispersion of sparks and improvement in the discharge characteristics, especially in the machining of a large workpiece. Okay, the introduction of mixed powders as working media allows abrasive electro discharge machining (AEDM) to produce complex shapes having a mirror finish and an affected layer which is uniform and free from cracks. Okay, let us discuss one more time. The introduction of mixed powders as working media allows AEDM to produce complex shapes having a mirror finish and an affected layer which is uniform and free from cracks. Okay, right. Let us discuss the uses of AEDM. AEDM, that is abrasive electro discharge machining, is widely used to produce dies without the need to remove the heat affected layer using mechanical polishing. Okay, so here, without affecting the heat affected zone. Okay, that is the important. AEDM is widely used to produce dies without the need to remove the heat affected layer. So the need to remove heat affected layer using mechanical polishing. The process is therefore widely used for producing plastic molding dies. So here a very particular application of AEDM is that produce plastic molding dies. Okay, why? Because here it is not necessary to remove the heat affected layer using mechanical polishing. Okay, without the need to remove the heat affected layer using mechanical polishing. Right. let us discuss on surface modification of materials. AEDM is also adopted to modify the surface characteristics of tool steels. Okay, so here last presentation also we have discussed on the tool steels and the tungsten carbide. Okay, so here AEDM is also adopted to modify the surface characteristics of tool steels. The fine tungsten carbide powder added to the dielectric adds alloying elements and hence enhances the hardness and corrosion resistance of tools and dies. So by this way we can modify the surface of the materials through this AEDM. So it is particularly used for tool steels and die steels, for tools and dies. Right. Surface modification of materials for the other materials. Okay. Right. It also improves their tribological features and changes the surface roughness. Okay. So here tribological refers to wear and corrosion, wear and friction of the materials. Okay, right. Deposition of aluminum on steel and titanium carbide on aluminum using respectively aluminum and titanium based alloy electrodes. Okay, deposition of aluminum on steel and titanium carbide on aluminum using respectively aluminum and titanium based alloy electrodes. So here the electrodes are with aluminum and titanium based. Okay, these can be surface modified with aluminum on steel and titanium carbide on aluminum. Okay, right. So these are the references for this. Powders such as silicon and tungsten have been used to increase the hardness and corrosion resistance of steel workpieces. Okay, so that's why the powder coatings will be applied for these materials. Okay, powders such as silicon and tungsten have been used to increase the hardness and corrosion resistance of steel workpieces. Right. Now let us look at this working of EDG schematic. EDG means electro discharge grinding. Electro discharge grinding removes conductive materials by rapid spark discharges between a rotating tool and workpiece that are separated by a flowing dielectric fluid. Okay, see here, this is the rotating tool. Okay, workpiece, it is controlled by servo control mechanism. Okay, for the feeding towards left or right. Right. Here the spark generates between tool and the workpiece, and the dielectric fluid medium is constantly supplying between rotating tool and the workpiece. Right. Here the power supply is DC. Okay. Tool is connected to negative terminal and workpiece is connected to positive terminal. Here the spark generates between the tool and the workpiece. Okay, here the tool is non-abrasive metallic wheel. It is nothing but it is a plain rotating wheel. Right. The spark gap is normally held at 0.05 0.0132.075 mm. Okay. So it is 0.075 mm is the maximum spark gap. It is less than 0.075. Okay, that is the maximum 0.075. Okay, here the spark gap is normally between 0.0132 to 0.075 mm by the servo mechanism that controls the motion of the workpiece towards left and right side. Right. Electro discharge grinding. The DC power source has capabilities ranging from like this: current 30 to 100 amperes, frequency 2 to 500 kilohertz, voltage 30 to 400 volts. Let me reiterate: the current parameter, that is in between 30 to 100 amperes, frequency is in the range of 2 to 500 kilohertz, and the voltage the range of 30 to 400 volts. Right. Now let us focus on the speed parameter, speed of the rotating wheel or tool. Okay, here the rotating tool must be conductive one. It is usually made of graphite. Okay, and its speed is 30 to 180 meters per minute. Speed of conductive wheel, usually made of graphite, rotates at 30 to 180 meters per minute in a dielectric bar of filtered hydrocarbon oil. So here the dielectric fluid medium is hydrocarbon oil, which is filtered. Okay, right. It should be filtered since during the machining the particles will be removed from the material, and these materials will mix to the dielectric fluid medium and the abrasive particles. Okay, so in order to separate this one, we have to use filters. Okay, electro discharge grinding is a common one, but here the power supply must be DC one. Okay, and the workpiece is connected to the positive terminal of the power supply, and the tool is connected to the negative terminal. Okay, right. Here the spark or electric sparks, stream of electric sparks will generate between the rotating tool and the workpiece. Each spark discharge melts or vaporizes a small amount of metal from the workpiece surface. This is nothing but electro discharge evaporation. Okay, so this is due to the only spark between the tool and the workpiece. Okay, right. Here, no abrasive particles issue here, only because of the spark between tool and the workpiece. Here, electro discharge evaporation phase will come into force to remove the material from the workpiece. Okay, right. Here, current is the important parameter. Okay, so if we have higher machining currents, okay, produces higher machining rate. Okay, but it produces rough surface finish and a deeper heat affected zone in the workpiece. Okay, in other words, less machining current produces low machining rate but smoother surface finish and less damaged surface will be produced. Okay, so here the current increases, obviously the machining rate will be faster, but we do not get smooth surface finish. Rough surface finish only we will get, and a deeper heat affected zone will be formulating in the workpiece. Okay, but less machining current is used for production of smoother and less damaged surfaces. Right, now let us come to frequency parameter. Current parameter is 1, the frequency parameter is the 2. High pulse frequencies makes smoother surface. Okay, exactly reverse to this current parameter. Okay, if current parameter increases, what is happening? Rough surface finish only will get. But for frequency parameter, the frequency parameter is higher one, smoother surface finish will be produced. Okay, right, right. Now let us focus on the wear of the wheel. See, when the rotating tool is trying to remove the material from the workpiece, it will be subjected to some considerable wear. That it will be ranging from 100 is to 1 to 0.1 is to 1 with an average of 3 is to 1, depending upon the current density, workpiece material, wheel material, dielectric fluid medium, sharpness of corner details. Okay, wheel weight ranges between 100 is to 1 to 0.1 is to 1 with an average of 3 is to 1, depending on current density, workpiece material, wheel material, dielectric fluid medium, sharpness of corner details. Okay, so these parameters influence the wear characteristics of the rotating tool and the workpiece. So obviously we need to remove the material from the workpiece, but at the same time the tool will also subject to some wear. Now look at this graph. In the x-axis, removal rate, that is in cubic centimeters per hour. In the y-axis, it is surface roughness in microns. Surface roughness is R suffix A. Okay. So here the relation between these two is not a straight line. Okay. Right. See here at this surface roughness, the removal rate must be this one, but it is little lower. Okay, why? Because it is not straight. Okay, similarly here it is okay, but here if we take this one, if it is straight one, the surface roughness would be something higher, but the surface roughness is somewhat lesser here. Material removal rates range from 0.16 to 2.54 cubic centimeters per minute, and surface finish in the range of 1.6 to 3 microns are possible. Okay, so however, we have discussed the relation between these two, surface roughness and removal rate of the electro discharge grinding process. Right. Surface roughness improves with an increase in pulse frequency and is typically zero point 0.4 to 0.8 microns. Already we have discussed. Okay, regarding pulse frequency. Okay, regarding current, the current increases, we will get rougher surfaces. If frequency, pulse frequency increases, we will get smoother surface finish. Okay, if current increases, we will get rough surface finish, but if frequency increases, smoother surface finish we will get. Now look at this elements of electro discharge grinding. So it is a simplest form of machining, electro discharge grinding. Okay, here EDM, this will be with electro discharge evaporation phase, it contains plasma. Okay, so here the metallic wheel, okay, and the workpiece dielectric fluid medium will be circulating between the tool and the workpiece. The tool is connected to positive terminal of the DC power supply, and the metallic wheel tool is connected to the negative terminal of the DC power supply. So here the spark will generate between the tool and the workpiece. So this gap is nothing but spark gap. This is usually 0.03 to 0.075 mm. Okay, right. In abrasive electro discharge grinding, it is AEDG. Abrasive electro discharge grinding AEDG employs the interactive effect of these two, EDE and MA. EDE is nothing but electro discharge evaporation. MA means machining by abrasion. Okay, so EDE means electro discharge evaporation. MA means machining, INING, machining by abrasion. Okay, these two phenomena involve in abrasive electro discharge grinding. Okay, right. In the abrasive electro discharge grinding process, the metallic or graphite electrode used in electro discharge. Okay, so here the focused points or takeaway points are these two, EDE and MA. EDE means electro discharge evaporation, MA means machining by abrasion. Okay, these two combines so that it will be abrasive electro discharge grinding. See here, in place of earlier simple or plain rotating tool, here we have metallic bond abrasive wheel. Metallic bond abrasive wheel. Okay, right. Again, same. Here the tool rotates. Okay, and the workpiece will be controlled with servo controlled feed mechanism, and the dielectric fluid medium will constantly circulates between tool and the workpiece, and the tool is connected to the negative terminal of the DC power supply, and the workpiece is connected to the positive terminal of the DC power supply. Here the spark generates between the tool and the workpiece. Here the tool is said to be cathode and the workpiece is said to be anode. Okay, right. Here let us discuss the material removal mechanisms in abrasive electro discharge grinding. See here, focus on this one, metallic bar. Okay, so this is metallic bar one. This is abrasive grind. Okay, so here these abrasive grinds will directly remove the workpiece material, and this metallic bond and the workpiece will not come in contact directly, but spark will generate between these two, and this spark will melt or vaporize the small amounts of workpiece surface material, so that the material removal process will take place. Okay, right. Right. Regarding performance measures, an increase in performance measures of the machining process becomes evident with machining super hard materials, engineering ceramics, sintered carbides, and metallic composites. Okay. Right. The electric discharge causes considerable decrease in grinding forces, lowers the grinding wheel wear, provides an effective method for tracing the grinding wheel during the machining process. Right. Now, look at this material removal rate for the EDG versus AEDG. EDG means electro discharge grinding. AEDG means abrasive electro discharge grinding. Now let us compare. Okay, the relative material removal rate for EDG and AEDG process was compared to the material removal rate for the electro discharge process under the same conditions. Right. The increase in productivity of the EDG process is attributed to improvements in hydrodynamic conditions of the dielectric flow. This improvement results from the number one, rotation of the wheel electrode partly by its radial oscillations. One is rotation of the wheel electrode, okay, and partly by its radial oscillations, okay, radial oscillations. Further improvement in EDG performance characteristics can be achieved with the use of vibrating electrodes. Okay, the third one is if it vibrates, then also it adds some additional removal rate. Okay, So by this way, we can compare the performance or the material removal rate. Right. Right here, look at these elements of abrasive electrode discharge grinding. So here, this one is divided into two main lines. One is grinding line, the other one is the basic machining, that is electrode discharge machining. Right. In grinding, the MEA phase, that means machining by abrasion phase with abrasives, and in EDM, electro discharge evaporation phase with plasma. These two will combine and formulate an abrasive tube that it will strike directly and indirectly to the workpiece to remove the material. Okay, so here the tool will not come in contact directly, but the spark strikes. The abrasive particles will strike. Okay, right. Right. Now let us compare the material removal rate among these three: EDM, EDG, and AEDG. See here, material removal rate will be higher for AEDG. Okay, in the AEDG it is 5 times that of electrode discharge machining. That is the basic one. Okay, compare to this AEDG, EDM is very less performed one. Okay, AEDG is 5 times that of the EDM. Similarly, AEDG is 2 times that of the electrode discharge grinding. Okay, right. As the number of wheel revolutions increases, the effect of abrasive action is also increases. Okay, that means if we increase the speed also, then we can increase the abrasive action, and subsequently the material removal rate will be higher. Okay, that means the speed of the tool increases, then the material removal rate will also increase. Right. Applications of EDG and AEDG. Steel and carbide at the same time without wheel loading. Thin sections on which abrasive wheel pressures might cause distortion. Brittle materials or fragile parts on which abrasive materials might cause fracturing. Farm tools and tungsten carbide throwaway bits for which diamond wheel costs would be excessive. So these are the applications of EDG and AEDG. Now let us conclude with references. So these are the references. Thank you. Okay.
Like, share and subscribe. Hit the bell icon for more updates.